Hey everyone, it's time for some activity, so let's just jump into it. Here we go. Gonna make the font a good bit bigger. We had, Connor. Maybe I didn't change it. I didn't close out R today. Yeah. Got my ARG ready to go. We got some activity 11. And here we go. So if you're in the chat, feel free to let me know. But let's start going through this right here. And we got question 1. Use the data command to load in the data frame junk. So the junk data set is part of the reg class data set. This is whether or not an email is junk or safe. And we're looking at the frequency of symbols in the email. And we got all these different metrics right here telling us how often these things occur. So you have to make sure you have reg class on. Start as reg class and then data junk. Now, the reason you'll know this is in the reg class data set is when you type it properly, you'll see reg class right there. So this is a reg class data frame. Any sort of data frame will tell you what it comes from. Like, do I have the AUST data on? I don't have it. This is just another example of using a different data frame. Watch this. When I type data and I type Australian, you don't get the data sets I'm looking for until I go and load the libraries, which you probably don't have these, but I'm just showing. FPP3 is a library I have for the forecasting principles and practices. And now if I go data and load the Australian data, we get ones from the Australian data sets. It also loaded in other libraries. So the reason you wouldn't have these is because you don't have these libraries, or you could get them if you want. But the reason you do have the junk data set right there is because you have reg class. So that's loading a data set that reg class, the package we have, gives us. So right here we have the naive model. Let's see right here, we're predicting safe because it becomes last alphabetical. And let's think about how the naive model predicts. The naive model predicts every email to be the majority level. That's a huge note right there because we're predicting a categorical variable. Run summary, which level of junk or safe is the majority level? What is the misclassification of the naive model? Really, really great questions right here. Just walking through. So we need to put in our chunk really quick. We'll call this 1A. We can go back to it anytime if we want, going to 1A. And let's go here to summary of our junk data, $junk. One of the confusing things about this data set is the data set is called junk, and then there's the variable inside of it called junk, which is a 2-level categorical, so we can do logistic on it. Now, if you notice right here, most emails are safe. This might be an older data set, right? Most emails are safe, and 1,813 of them are junk. So what we can actually do, I'm not going to use this summary as it says I'm going to do a table, which gets you the same output. I'm going to divide by the number of rows in the data set. And now we can see the percent or the decimal percentage of the emails that are safe. So when you think about this, and we can do one last thing right here, we're seeing what percent are safe emails, and 39.4 are junk, and 60.6 are safe. So the model would predict everything is safe, not because safe comes last alphabetical, but the model predicts for the naive, the majority level, like if we're doing the naive model. So it would say everything's a safe email. So it would get this much correct and it would get this much wrong using the majority level. And that's what the naive does for categorical. Now, don't confuse the naive for categorical with the naive for quantitative, because the naive for quantitative will use the mean of y, which this does not have a mean because it's a category on whether an email is junk or if an email is safe. So the naive model would get wrong 39.4, and that is the misclassification. The accuracy of the naive model is 60.6 right here. Last but not least, if we want to make this look a lot better, we're going to throw inside of a round right here. We're just kind of nesting our function right here. And then we get the following values. So this is the misclassification and the accuracy in percentages. A particularly strong association between the probability of being junk and the frequency of the word is the frequency of the word free. Fit a simple logistic model, like if someone's like free this, free this, free this, this is going to be highly associated with an email being junk. Fit a simple logistic model, and we'll get a warning right here, which is fine. Run the summary, visualize model, and confusion matrix on it. Okay. So we want to predict if an email is junk from the word free, how the frequency of it, data equals, and usually, and we see this especially with the take home, people forget family equals binomial. Now I like to hit enter right here just to get another space on my code. Here's the formula, y tilde x, data equals, and then you can hit enters to just kind of read through and get things on separate lines, and the function should run. And it says free not found. Is free lowercase? It is lowercase. That's why. Now we find it. Warning, fitting right here, 0 1s. So this is because it's binomial. That's quite fine. Don't worry about the warning. If you really, really wanted, you could probably go in front of this and do the following. Suppress warnings. You don't have to do this, but, oops. Suppress warnings. And I'm betting, oh, no warnings. That just removes the warnings on it. You don't have to do that, but we no longer see those warnings. Just a nice thing you can do. Let's go ahead and look at the summary of our model right here and think about what we have. Now, we're predicting the probability of something being safe because safe is last alphabetical. In logistic, the level of interest is last. Level of interest means what you want to see. So think about as something, an email says free, 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 the probability of it being safe would do what? Just think for a moment. As an email says free this, free that, free everything. You're like, is this a safe email to me open when it says free, 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 free in the title? You can kind of see some of the body email. You're like, free this, free that. You're saying my probability of it being safe is going down. The coefficient is negative, implying that two emails that are otherwise identical, it's not a multiple, we could say that. Two emails that differ in the amount of frequency of the times they say free, the email that says free more often is less likely to be safe. This is even more clear with the visualization of the model right here. And when you look at the visualization of the model, you'll notice we get, as the frequency of free increases, the probability of it being safe decreases. Now, this is not constant, so do not interpret this coefficient. You wouldn't go in and interpret this coefficient and say two emails that differ in the frequency of free by a certain amount, one frequency, we'd expect them to be differing in their probability by this. No. Once again, the interpretation is two emails that differ in their frequency of how often they say free. The email that says free more often is less likely to be a safe email. It's more likely to be junk. So it kind of makes sense with our world that if an email says free more often, it's probably not a safe email. It's less likely to be safe. Less likely. Now, we can't say it isn't safe, but it's friends like, hey man, free food. And you're like, not a safe email. Well, I mean, maybe it's not. So how does our model do? Well, we know how the naive model did from earlier on, but our model makes predictions. Our model predicts these emails are junk. Our model predicts these emails are safe. So our model would get correct this, and our model would get correct this. This is what's called the on diagonal, because these are predicted junk, and they're actually junk. These are predicted safe down here, and they're actually safe. So you want to think of this as the on diagonal. I got some tool 1 right there, but let's go take a look at this and just draw it to make sure people see it. The on diagonal is where these match up. Things that are predicted junk and are actually junk, things that are predicted safe and are actually safe, that meet right there. So now we just add them up and we divide by the total. So how many does our model get correct? 638 plus 2661 divided by 4601. That is the percent our model gets correct. How much better than the naive is it? I don't know. So this is the accuracy of our model. Let's say accuracy. And then 1 minus accuracy is the misclassification. And that's what percent our model misclassifies. And you could also find this by just doing the ones that are called the off diagonal here, where we predicted something is junk and it's actually safe. So we sent something to spam folder and we shouldn't. And these are emails we thought were safe, but they're not. So that's bad. And you can see we get the same number right there to the same decimal place accuracy. So just making sure you understand where the accuracy of your model comes from. You predict something is junk and it's actually junk. You predict something is safe and it's actually safe, versus misclassification where you predict something is junk and it's safe. You predict something is safe and it's junk. So we have all that right there. True or false, the emails that contain a higher fraction of the word free have a higher probability of being junk. Correct. Emails that have higher fractions of the word free have a higher probability of being junk because they have a lower probability of being safe. So higher probability of being junk is lower probability of being safe. So more free, higher fraction of the word free would have a higher probability of being junk because they have a lower probability of being safe. How many junk emails were correctly classified as junk? So now we need to know of the actual junk emails. So here's the actual junk emails. How many of them were correctly classified as junk? And there's the answer right there. Of the actual junk emails, how many of them were classified correctly as junk? 638 out of the 1,813. how many safe emails were incorrectly classified. So these are the actual safe emails. Like these emails are safe. And the ones that are incorrectly classified as junk are these right here, 127 out of the 2788. And we did get the misclassification rate, which would be these two numbers right here. We added them up, and we showed the other way by finding the accuracy, but the misclassification rate of the model. Let's do a pause right here. That's a good pause on the first question right there, but just walking through, understanding how to make and build these models, and understand that we're predicting probabilities is kind of the key to this. So let's take a look at the next question. Check the validity of the simple regression. Oh, I love it. With an associated and check regression. So this just wants us to look at the associate first. So we're looking at junk tilde free comma data equals. This doesn't use family binomial, and we'll go here to junk, and there we go. It's going to make the graphic for us real quick. It's going to make a mosaic. Oh, is it mad? Factor 2 level is duplicated. Dun dun dun. Free junk y tilde x comma data equals. What is going on? Error in 2 levels. Factor level 2 is duplicated. Well, that's odd. I don't like that right there. Should work. Might reset R. You'd be amazed at what an R reset can do. Let's try a reset of R. It's funny, I was in another class and I was like, something wouldn't work for about 10 minutes. We reset R and it worked. It's the way it goes sometimes. And let's go back to the question. Here we are on the question. Let's try it again. Data equals junk. We need to load up our library reg class. And load up the junk. There we go. Associate. And junk. Free. Oh, we can't use free like that. We gotta use free like this. Maybe that was a problem. Should have looked at my code a little bit more. Data equals and capital junk. Oh, it's just saying no. Let's look into that. Associate. Should have ran. Check the validity of the regression. We have everything properly spelled. Y tilde x comma data equals. Associate should work. I'll be. As categorical. Oh, is it really? I think I know what it's mad about. Well. It's mad about one of the error in levels temp as character levels. Factor level 2 is duplicated. Well, I'll have to take a look at that. It's just saying no between one of those tests. Y tilde x. I wonder if. Let's do the following. This will do about the same. Similar ask, and it's actually going to run this time. We're comparing the means between the groups. Different right here, and yeah, it has to do with one of the way it looks to be creating it. That's fine right there. Yeah, there definitely is an association. But the big thing, I'll have to look at why that code's not running. That's an issue. The check regression right here is going to come back and tell us if this model we created previously is appropriate. And we don't have our model anymore. We're going to have to go remake it. Let's remake our model right here and see if we should be making this model. So when we run this right here, it's asking us, should we be making this model? Oh my gosh. Oh. There we go. And one thing I want to point out, ooh, that's fun, is when you do this, especially for the take-home, you will have to run a set seed. This is coming back with a very bad value. This right here is not good news for us. This p-value on this check regression points to the fact that this model is not the proper fit for the data. And what model are we talking about? We're talking about this logistic curve we fit earlier on. So this logistic curve right here that goes through the data like this, it's not the right curve. And why do we know that? The p-value here is low. The null hypothesis is that the logistic curve, the sigmoidal S shape, is actually a good fit. You might say, well, Brian, that's not an S right there. Let's go to the X lim and set an X limit right here equal to -2. Oh, I'm going to -5 all the way to 5. And you should be able to see a little bit better that this is a sigmoidal curve. You can't have a negative frequency, but this sigmoidal curve right here is not the pro either or. Both of them are screaming at us, no, this is a bad idea. You have fit the wrong curve. So that's not a good idea. Even when the logistic curve does not provide a reasonable description of reality of how the p-value changes with x, the probability changes with x, the model may still be more useful than the naive. In that sense, it makes more accurate predictions. Does the simple logistic model get more predictions correct than the naive model? So once again, what we want to do here is we want to compare our model to the naive model. So let's go ahead and once again show how to get the naive. We want to go here to a table of the naive, which is going to be junk and junk, and the naive gets this many wrong. So the naive would predict everything is safe. So wrong from naive. Our model, we need to look at the confusion matrix, gets wrong these ones right here. These are the ones it predicts junk that are actually safe. And then it gets wrong these here where it predicts that it's safe and it's actually junk. So you know what? Yeah. Our model misclassifies 1,302 emails where the naive misclassifies 1,813 emails. It's a pretty big difference. I think it's around a 10% difference or 6. We could find the percent differences right here, but this is a very, very large difference. Let's find those differences in percentages by taking the number and dividing by the total. The naive gets wrong this percent. So there's that for the naive, and our model gets wrong. Yeah, it's more than 10%. It's just a little bit more. So that's a good bit of a difference. Probably if I'm explaining this one, I would say it's about 11% less misclassifications, going down from about 40% to 28% or 39%. Yeah, it's a pretty big difference. We cut down the misclassifications a lot here, and this is because the naive just classifies everything by the majority level. Now fit the full model using all predictors, no interactions using the twiddle dot. And so let's go ahead and take a look at this here. We're just going to grab our code and use the twiddle dot. Let's go down here, fit the full model. Just add in the dot. And here's our full model. And once again, we get the same little issue right there, but that's fine. We got our summary. And here's all the coefficients. We get a lot of coefficients now because there's a lot of x variables. Here's every single coefficient, a lot of statistical significance, which is good. And then we want to run a check regression to ask, are we fitting a good model? Should we be doing this? And the answer is most definitely. I think I know how it's going to go. Yeah, the answer is no. The answer is that this model is not a reasonable reflection of reality, which is a bit of an issue. This is not good that you're not having good assumptions passed, but we might still look and say, well, how does the model do? So let's go to the confusion matrix to ask how the model does. And remember, whenever you look at this, you want to see what the model gets wrong. And actually, wow. Owen Wilson, where are you at, man?
Wow.
This model only gets wrong these. We might be running into the realm of overfitting, though. This is all the model gets wrong right here is 316. Those are the amounts the model wrong from this model. And that would be out of the total. So 316 divided by the total right here is about 6.8%. So this model right here does extremely well. Is it overfit, which means we've probably put too many X's in? Maybe. I don't know. We'd have to be running some more statistics on it, but overall, this model right here looks to have issues with how it's fit. The model does extremely well on the data, and the model has a lot of variables in it. I'm kind of worried about this model. I'm a little bit worried. Among emails with otherwise identical characteristics, frequencies, capital letters, and all that stuff, do emails with a higher frequency of semicolons have a larger or smaller chance of being safe? So remember, if something has a negative coefficient, it's going to decrease the probability of being safe. So let's go to semicolons. Semicolons in this output right here are right here, and they have a positive coefficient. That means two emails that are otherwise identical, if the email has more semicolons, then having more semicolons will increase the probability of an email being safe. So we're not saying add semicolons in your email is safe. We're saying we have two emails. They're like identical emails. Every word in them is the same, except that one has more semicolons than the other. And actually, the frequency of semicolons being increased between two identical emails makes us say the email's more safe. And that's actually statistically significant, which means it's adding new information. So yeah, definitely. Is the association statistically significant? Definitely. And it would lead to us thinking it's more safe. Do not interpret this coefficient. Oh my gosh. Do not interpret that coefficient right there. Two emails that are otherwise identical, but one has more semicolons than the other. The one with more semicolons is more likely to be a safe email. Is the variable make statistically significant? Where's make on this output? Oh my gosh. Make is all the way right here. Nope. It is not statistically significant. Fit a simple regression model using junk from make and verify its significance is the opposite of what you found in the full model. And is there an association between the probability of being safe and the frequency of the word make or not? Well, you don't need to answer anything here. You should be able to explain why this happens. Yeah. So why does this happen? Because let's go make the model and show this. If we go and make a model with just make in it, what we're examining is, does make explain in some way the email being junk or not? The word make and the frequency of the word make. So if we go and look at this, the frequency of the word make is super significant. It's ridiculously significant. So we're going to see a very steep sigmoidal curve right here. So here's a really steep, yeah, it's good enough. A little fun sledding hill. Whee! This is very, 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 very statistically significant. So then the question becomes, why in this model is make not statistically significant? So you see it's not statistically significant here. And this goes to the world of multiple regression. In multiple regression, you must bring with your variable new information. As you go into the model, you're competing with these other variables to explain the y variable. So if you don't bring new information, you're not significant. Now, in the simple world by itself, it has information, but due to probably overlapping, we don't have our multiple models saved. We could look at the variance inflation factor. We would have overlapping between the x's right here. And let's go ahead and look at that for the multiple model. Let's go VIF, should be capital VIF. Does make have high variance inflation? Probably not that high, but there's a little bit of variance inflation. There's high variance inflation down here with the following variables, which show extreme overlap with that capital variable with maybe other things like capitalization is overlapping with other, like these two variables, probably a lot of overlap. So you don't want that. You don't want your x's explaining your x's, because then that can lead to the x's not being able to be significant in the model. So big stuff right there. Does the multiple, did we go right here? Here we go. Does the multiple logistic regression model provide a statistically valid description of how the probability of being safe varies with the predictors, regardless of whether or not it does? Is the model useful for making predictions? Justify your answer with the goodness of it and misclassification. So we're going to go right here and make our model again, and let's see how it does. Now, I don't have good faith in this because it's going to predict. Aloha, Diddle. Great to see you. Chloe, great for being here. Yes, send it. I probably will have time. I'll try to look. I'm going to eat some dinner here and then probably look at some emails. So I probably will have time to send it as quickly as possible. I'm more likely to see it there. If we want to see if our model is a good fit, we're going to go to the check regression to see if it actually is a good fit. And the answer is no. Well, one friend says no, one friend says yes. So we got conflicting results. One friend says no, one friend says yes. And that's not good. I'm a little worried. It's better than both friends saying bad. This friend said bad fit. This friend said okay fit. I'm a little worried right there. You're welcome, Chloe. And confusion matrix. The model right here, let's look at how it predicts. It gets these wrong. And it gets these wrong. So, no, wait. That's not going to be right. Ooh. Whoa. That can't be right. Can't be what it gets wrong. Oh, I did it out of the wrong total. That's why. I was like, that doesn't make sense. 38%. Ooh. Oh. What was the naive's probability again? Percent wrong from our model is this. And the naive all the way back up here. The naive got this. Wow. That's not good. That's not good. This model compared to the naive is very similar. The naive model. So if you look at this, it does only a little bit better than the naive. I kind of noticed that because only down here would we predict it's safe. So yeah, this model overall, it's barely better than the naive, Definitely not the best of models right here. So yeah. Does the multiple logistic model provide a statistically valid way to describe? Nope. Does it help us make better predictions? The answer is yes. So with the multiple model up here, the reason we know it's not statistically valid, and this one really has a problem with the assumptions, is because the check regression on the multiple comes back with a p-value of 0. But the reason we might say it's a decent model, but we're really worried about its assumptions, are it only has this many misses. It has very few misses, which is only around 6%, which when you compare that to our other models and how much they miss by, like the ones they get wrong, the other models do way worse. So a little bit worried about that. Does the multiple... Yes, we did that one. Interactions. So let's pause right here, put a cut in the video. Interactions are a pretty big topic. Interactions are the way in which x1 explains y depends on x2. So now we're going to allow for some variables to interact right here, and it'll make the logistic curve have a different bend depending on the other variable. So let's take a look. Interactions may play a significant role. Without interactions, then the curve will be constant, the same shape across. And now we're going to allow for some interactions between the variables, make them all predicting junk from u and direct along with their interaction. Okay. Oh, we don't have the model saved anymore. Let's go grab our model. Nice, easy way. Just calling all of our models M, just overwriting them. And let's go here to U and then make the interaction between the two and go direct. To make an interaction, do the multiply to them and you get it. Let's go ahead and do a summary of our model. And here's a summary. And the interaction is statistically significant. That's going to make the curve bend differently depending on different levels of x1, how it explains x2, or how it explains y with x2. So let's visualize the model right here. And here we are. Now, one thing we can do right here, there's the x-limbs, yep. Let's go here. And x-lim from -15 to 15. And whoops, concatenate that vector. X-lim equals concatenate. There we go. And I'm going to do the following. Loc equals, yeah, let's go left. There we go. And then let's expand. And there we go. Nope. There we go. Cool. Okay. So what do you notice right here? The interaction is actually so significant that if u is set a lot, direct actually lowers the probability of it being safe. Where if u is barely ever set, if people say u a very small amount of times, then direct increases the probability of being safe. So you would say the more u is said, it actually creates a negative relationship with being safe with direct. So if you notice, we can't really go through 0, but it helps us kind of see the curve a little bit better because this is frequency of words. It would technically start at 0, but the relationship with what direct does to the probability of being safe depends on u. The relationship with direct and being safe depends on the frequency of u. For very small levels of u, direct would increase the probability of it being safe. For very high levels of u, direct will decrease the probability of being safe. So how does direct explain the probability of an email being safe? Well, it really depends on how often u is said. The more often u is said, then direct will start to have a negative probability. At some point, u having a very high amount of occurrence would actually make it so direct would make emails less safe and more likely to be junk. So this is what the interaction does. It makes it so that the way in which x1, one of these variables right here, explains y, depends on x2. This is the other relationship here, but it's more clear to see over here the way in which direct is impacted by u when direct is explaining safe. So these are implicit sigmoidal curves being shown for you right here. Is the interaction statistically significant? Well, yes, it is. And there's the p-value all across. So the p-value right here, is it calculated a little bit differently? I think it is. It might be doing like a drop one type test, but it is very statistically significant. We see statistical significance with the p-value right there. For what values of direct, small, medium, or large, does the relationship between the probability and u change the steepest? When it goes from medium to large, definitely there it is right there. And what is it the steepest right on? The steepest relationship looks to be small, and that's the most extreme relationship right there. But it's also in competition maybe with large. But nah, small, yeah, it does. Small is the steepest. That's the most extreme relationship we see right there. When an email does not have the word u in it, u equals 0, what types of emails are most likely to be safe? Oh, So that'd be a very small amount of use. So it'd be on this right here, very small amounts. So the emails that are most likely to be safe are the ones that say direct a whole bunch. Because if it has a small amount of you in it, then you'd want a bunch of it saying direct. You'd want a high frequency of direct, and that's a very likely safe email. So just following that line right there for the small u, and then going up and going over. Describe how the nature of the relationship between the probability of being safe and frequency of the word direct changes as we consider emails corresponding with larger and larger values of u. So I think we were talking about this earlier here. If you look at u going from small, it has a direct has a positive relationship, which means direct would make emails more safe if u is very small. But as you go to larger values of u, direct starts to get a negative relationship and make emails less safe. So it totally flips the sign of direct going from small to large, where direct originally has a positive coefficient for the blue line right here, sigmoidal curve. And then as you increase the amount of frequencies of u, direct starts to have a negative relationship for very high levels of u. Refit this model without the interaction and visualize it. Notice how the model implies that the probability of being safe increases with direct, regardless of the values of u. So we're going to do the same thing here, and now we'll get parallel sigmoidal curves. The reason they're parallel is because there is no interaction term. Without the interaction term, the relationship right here is going to be constant. Whoops. So now we notice a constant relationship. We're going to go here and just make this a little bit larger with the x lim. And let's go to -5, 8. There we go. I'll go to -8. There we go. And if you take a look, these sigmoidal curves are actually parallel. So direct actually increases the probability of an email being safe, and it's the same for any value of u. Previously, we had differing relationships, but because there is no interaction term, these are actually parallel. You might say, well, it looks like they're starting to meet. It's just because the curve bends. They are actually the same shape. We'll go a little further out so you can kind of see that all of these curves have the exact same shape to them. And you can kind of see it a little bit better here, that they're all the exact same curve, just kind of moved over a little bit, but they still have the same sort of steepness to them. And what is changing the steepness is the interaction term. If you add an interaction term, now the relationship direct has with u depends on the level of u, or excuse me, direct has with probability of safe. So the interaction term is what creates here the difference in the slope of the sigmoidal curve. The slope will have a different bend to it with the interaction. Here's with the interaction, here's without. Without the interaction, they're parallel, like lines would be parallel. Let's put a pause in here. If you have questions, let me know. We've been going for about 30, 40 minutes, I guess, right now, right? We're going to load in some EX9 data. Let's go check out that EX9 data. Loading in the EX9 data using the data command. This data set was created by a bank that was studying whether or not associates between shopping at one store or another. It's real data, as the store names have been anonymized. Fit a model predicting store 68. Levels are buy, no. From all other predictors, each are the buy and no variables on whether shoppers may purchase at those stores, since no comes last alphabetically. So once again, we're predicting the variable and it has buy or no, and no is last alphabetical. That makes it the level of interest, and you'll see that over here on the axis telling us what variable we're predicting. Let's load in the EX9 data. There's the EX9 store data. And let's go here and predict. I think it said from all variables, right? From all other predictors. That means we're doing the twiddle dot data equals EX9 store, and family equals binomial. And there it is right there. Now let's go ahead and summary the model. And the model looks to be, it's got some stuff in it, but a lot of these variables are not significant. But we're using a lot of categorical X's right here on whether or not someone purchased at another store. You know, store 64 is like no, because that is an indicator indicating someone did not purchase at a certain store. So how does our store get impacted by other stores right here? So since no comes, yep. Among two otherwise identical shoppers, buying habits, they both shop at the same set of stores and not shop at the same set of stores. Which one has a higher probability of buying at store 64? The one who buys at store 66 or the one who does not buy at store 66? So we are predicting the probability of not buying. So we'd actually want to see here a negative coefficient, which would mean it would lower the probability if somebody did not buy. So let's take a look. Store 66 is right here. And this negative coefficient means if someone does not purchase at store 66, oh, it was like triple negatives. If someone does not purchase at store 66, it'll lower the probability of them not buying. Okay. So not purchasing at store 66 lowers the probability of you not buying. So not purchasing at store 66, since it lowers the probability of not buying, it would increase the probability of you buying. So store 66, when someone does not purchase there, it would make them more likely to buy at the other store. So not purchasing at store 66 would increase the probability. Why does it increase the probability? Because these are people who do not purchase. It has a negative coefficient, so it'll lower the probability of not buying. So very triple negatives right there. Tricky question. By running the confusion matrix, comment on whether the multiple logistic model is useful. So let's go ahead and run our confusion matrix. And here's the amount we get wrong. Remember, the amount we get wrong is on the off diagonal. We were talking about that earlier, that we take the values right here and we can divide by the total. These are the ones we predict incorrectly, and I almost grabbed the wrong total. And we predict wrong 25%, about 25% if we talk to the leadership. But if we were to talk about this in general, we would take the totals. Let's do the naive model here, and we'll do a table. And we're predicting store 60, which one again? Store 68. So a table of store 68 from the EX9. There it is right there. And let's divide by the number of rows. It looks not great, but not horrible. Our model got wrong 24.7%, and the naive got wrong 31.33%. So our model's a little bit better, but I'd like to see a much better model. That's not amazing. How does the check regression look? And you want your p-values to be high on check regressions because check regression has the null that there is not an issue. And not the best of models, but it doesn't have issues. It doesn't have issues because the p-value here is high, indicating to us we do not reject the null hypothesis that the model is a good fit. The null is that the model is a good fit, and the alternative is that the model is a bad fit. And we're doing pretty good on that. Question number 3. So, not the best of models, but it passes conditions. It's kind of like we got a model that works, but it doesn't work too well. But at least it's not the wrong model. I mean, at least, what do we mean by wrong model? Like, fundamentally, we're not fitting the correct sort of shape through the data. Like, if a data goes like this and goes up and down, it's not monotonic. The sigmoidal curve is monotonic. So it'll be reporting back to us, you should not be fitting this type of bend through the data. You should be putting something else through the data. But our p-value here says we're fine. But the model doesn't work amazing. So it's like model that should be used that doesn't do great. Download and import the account data. I think I have this downloaded. Let's double check. And call it account right here. So we're going to read CSV and save into it. Let's see. Fit a model predicting. We'll go ahead and do that. Do we have it? Let me go get this file. Go grabbing the file from the activity. There it is, the account. Oh, it's got like all the ones and everything after it. Oy, oy, oy. 2 seconds. How is it currently stored on here? Count1.dat. Course files. Really? Let me check. Well, let's rewrite this. I've got it here. I take off all the... There it is. I don't know why it had a different file name. And let's fix that. And insert. should be. There we go. Really? Saying can't upload these files. Insert document, upload document. Okay, that should do it. Don't put any numbers on it. Let me go to course documents. Canvas is so mean. What? There it is. Okay. And let's save it. And should be good. It was not liking that file. Now let's try it. There we go. Good to go. Okay. Take off all the names and you shouldn't have any issues now. And let's go check it out. Calling it account. Oops. So the code is supplied up there. It's just reading a CSV. Strings as factors tells it that if it has a word, it's going to be treated as a categorical variable. And this is the name of the file name. You have to make sure that matches and it's in your working directory. If that's not there, big problems. Fit a model. Which model are we fitting? Fit a model predicting purchase from checking account and checking balance with branch of banks. Let's go do that. Save into M, GLM, purchase, tilde, and checking plus bank of purchase. Now we need to do data equals account, comma, family equals binomial. Should work. There we go. And we've read in the file. We fit the model. We really don't need... we probably need to drop one because branch of purchase probably has a lot of variables. So let's go take a look right here. Yes, it does. Look at all those bank locations right there. So the question would become, why would we use a drop one? Drop one is used, if you notice, we only put two variables in here. We put in checking balance, which is right here. It's quantitative, so it only brings in one coefficient. But branch of bank has a bunch of levels to it, multiple levels. It does it kind of alphabetically, so the 10 comes first. And then you get like the, where's the 1 at? Oh, is there no bank 1? Oh, what am I thinking? It's the reference level. There you go, it's the reference level. The other ones are the indicators. I was like, where's branch of bank 1? So this is in comparison to branch of bank 1, how the probability of someone making a purchase would differ. And so if we want to look at if somebody's branch brings with it new information, we have to run the drop one. And to run the drop one, you need to put in your model, but then do family, test equals, and then chi, capital C right there, square. If you don't spell chi-square properly, I think it just doesn't run it, and it gets mad at you. But it does give you the tips of how to run it. It's chi-square because it's categorical. It's a categorical Y, and branch of bank definitely brings with it new information. How do we know this? Well, because when you remove all of these indicators right here, it brings with it new information, and that's seen right here in the p-value. So very, very statistically significant. We could have told you checking balance was significant alone by looking at the p-value for checking balance, because that's just one variable. Branch of bank, we have to look at the drop one to see if it is statistically significant. Summary, we looked at that earlier. Visualize model. I guess we can do it, right? Ooh, it's going to be interesting, right? That's what I thought. Wow, that's cool. So let's go here to loc and go 9999. Good. And let's do xlim. Just such a pretty graphic. Good way to end with some beautiful colors right here. Let's go negative 50,000 to 200,000. And wow. Now the reference line is the black line. And we're predicting the probability of someone purchasing. So whatever bank this is, that's where people just don't make purchases. And then a lot of banks are close to the reference line, the black line in here. That's bank 1. You really got some stragglers in here. We could figure out which bank this is by the most negative coefficient because they have the lowest probability. So that purple bank right there is going to be, looks like bank 7, unless something has a way more negative coefficient. Looks to be bank 7. So let's see, purple bank, are you bank 7? And black bank is bank 7. What's going on there? Bank 7. Oh, look at if you notice, we've got here scientific notation trying to trick me with that scientific notation. So bank 2 might be the purple. There's so many close colors to purple. Looking at the negatives ones, this is okay. That's the most no. That's the most negative right there. -9 because the scientific notation is what's going to come into play right here. So I think it's bank 14. Yep, it's bank 14. I got tricked right there on the scientific notation because this right here, e to the -1, is going to be less decimals than the other ones. I was just looking at like absolute value of the sign right here, and I forgot its scientific notation. So this one right here is the most negative. It's this line right here. Bunch of lines piled up here with positive coefficients, but this line is the most below in probabilities. So 2 customers who are otherwise identical, but one banks at bank 1 and the other banks at bank 14. The person who banks at bank 14 is less likely to make a purchase than the person at bank 1. And yeah, we did not. Did we include interactions right here? Without an interaction, the model assumes that the one curve fits all. In other words, this. Refit the model now with the interactions. Woo! Get ready for some craziness right here. So now each sigmoidal curve will get its own bend. We're just going to grab all of our code. Now when we run this, we'll get to see if the interaction brings with it new information. And here is all the curves. We're going to go loc. If you do 999, it generally removes it off the graph. Woo! So now someone's checking balance. The way in which checking balance explains the probability of someone making a purchase depends on the bank they are at. There's actually one bank, whatever the green bank is right here, where someone having a higher checking balance would actually have a lower probability of making a purchase. And a lot of the banks have a very strong, you see a sharp increase, but the green one's the one that interests me the most. So we go look at that. There's a very, very strong interaction on that green bank. And the strong interaction on the green bank is probably looking for the strongest interaction right here from the reference. Because, got to watch out where the reference is because that'll control. Those are all the same right there. So it might actually be this one right here. It might actually be bank 11. It looks like it is bank 11. Is green bank 11? The answer is... It is bank 11. Being able to kind of see those things in the output is important because bank 11 has the most negative coefficient. Now, if you notice, there's only one negative one, but the other ones have a weaker relationship than the reference. The reference is in here somewhere. I think it's that line. I hate that it doubled it black right here, but the reference is the black line, and I believe it's that black line, and there's ones with weaker relationships than the reference. The weakest or the negative relationship here is seen by bank 11, which is behind my head right here. Bank 11 actually has a negative relationship, and that's bank 11 right there. I know you say there's 2 green lines, but this is bank 11 because it has a strong enough change to the sigmoidal relationship from what we originally saw of all positive relationships, such that now bank 11 can actually have a negative relationship right here. Now, the other coefficients are negative also, but that's because they have a weaker relationship than bank 1. So bank 1's sigmoidal shape, if it has a positive coefficient like bank 12, it would be steeper than bank 1, where if it has a negative coefficient right here, it would be weaker and flatter. And eventually, which only one did it, it became so flat that it actually went and became negative. So we actually see a very strong change to the relationship. Question becomes, is the interaction statistically significant? And the answer is most definitely yes. That actually runs the drop 1 for you right there, and you see the same p-value. So should we include the interaction? Oh, yeah, we should. I don't know if it asks us to do this, but we should. Let's go look at the confusion matrix. And how's our model doing? The model, if you notice, there's a lot of similar steps right here. You could think of this as lost opportunities, because if we predict somebody will not purchase and they actually did, ooh, it's a lot of lost opportunities right there. 10,000 lost opportunities. I don't know. So this model gets wrong 33.7. If we just did the naive model would predict every single person would not purchase. And the naive model, really? Yes, the naive model, I don't know how much better our model does. The naive model gets wrong 34%. While this model looks super cool, this model gets wrong 33.7%. The naive model just saying, well, no one purchases, gets wrong 34.6%. You might actually want to start looking in and saying, these are the people we would predict are purchasing right here. So if we did this, we would try to market to 983 people. We'd go and we'd be like, we should market to these people. We would only be right with these 983 people. Only 34.7% of them would make a purchase, which is very close to what we would. If you just chose random customers, 34.6% of them would make a purchase. If you use your model and you market to everybody you think would make a purchase, because you don't know when you're marketing if they're actually going to purchase, but you're like, let's go and market to these people. And you know from the data you trained the model on, but you're saying this model predicts this. The model is only correct on the people it predicts 34.7% of the time, because that's from the people it predicts. The percent of the time it's correct. And you would pick random people and be right 34.6% of the time. So in all, this model does not look too useful. Did we do a check regression on it to see if it's even a good reflection of reality? The answer is it a good reflection of reality? The answer is yes and no. So actually, this model right here, as fun as it looks and as cool as it is, this model doesn't look to do a lot of good work for us. And then the model might not even be a good model according to the low p-value down there. It looks like it has kind of issues. So this over here, it's like the fun with statistics that led us nowhere. But that's all right. So the way statistics is we make a bunch of models and we look at them. We have to know if we should use this or not use this. And overall, I think all this fancy number stuff would be the same as me just picking random people and them having about a 34.7% or about a 1/3 chance of purchasing. So I would say to the company, I'd say, statistical model doesn't come back with any really useful information. We'd have about a 1/3 chance about being correct if we use the model, or we'd have a 1/3 chance of being correct if we don't use the model. Check out 474 for some AIC or AUC. You know what? Should we do like a neural net on it? I don't know. We'll take a look. Check out some 474, but there's much more advanced ways to handle this, and maybe it would find the answer, or maybe it won't. You never know. Well, I'll talk to everyone later. We're done for today. Email me those questions if you got it. Bye for now, everyone. Bye.